Hello and welcome to my presentation called FluxCD Controllers in Kubernetes with Terraform. My name is Philip Lane. I work as a DevOps engineer at Senet. We are a Swedish-based company who helps customers with their Kubernetes deployments. I'm also a part of the Flux maintainer team, and I'm a HashiCorp core contributor. So this presentation will be all about how Flux and Terraform integrates with each other and how Terraform has simplified the installation process of Flux in Kubernetes clusters. To understand fully this presentation, I think we need some background into the different topics that we're going to talk about today. So first off, Kubernetes. Kubernetes is an open source tool that manages containerized workloads across multiple nodes. It deals with things like workload distribution, health checking, outscaling, and service discovery. So workload distribution is basically taking a container and placing it on a specific node based on the resource needs and other factors. Health checking is when it basically checks the status of an application and is able then to either remove that application from a node because it's not feeling well or restarting the application on the same node. Autoscaling features uses the cloud provider specific APIs to scale out a cluster and add more nodes when the need is there. And service discovery basically allows it to discover other applications and their endpoints in a simple manner. Kubernetes is configured through the use of something called manifests. So the Kubernetes API defines a spec, which you then use to create resources. These resources are defined in manifests. Manifests are basically YAML files that describe a desired state of a specific resource. There are multiple resource kinds. So the example to the left here is a deployment. A deployment is a obfuscation of a multiple replicas of an application. There are other types of resources like pods, services, and secrets. So all you need to know really is that to create a resource or to make something happen inside of a Kubernetes cluster, you would have to write one of these manifests and add it to the cluster. Custom resource definitions is a slightly newer concept in Kubernetes, and it allows you to extend the existing Kubernetes API to add more custom functionality while at the same time using the same type of way to define and create resources. This has enabled projects like Cert Manager, which has a certificate resource, so you can automatically provision certificates from Let's Encrypt, for example, by just creating a certificate resource in your cluster. CRDs are made up of two components, really. So one is a core resource called custom resource definition, which defines the API spec of your custom resource. And then there's the actual custom resource itself. So the image above is the custom resource definition. It has a specification of these are the parameters that are available in the resource. And the example below here is a Git repository resource, which is a custom resource added by the Flux project. So what is Flux? Well, Flux is a tool for keeping Kubernetes clusters in sync with sources of configuration. What that really means is that Flux runs as a daemon inside of your cluster. It pulls a Git repository for manifests. So it's constantly checking if there are new commits in a Git repository with new manifests there, and it will take those manifests and apply them to your cluster. Flux builds upon a concept called GitOps. GitOps, as an idea, turns continuous delivery on its head, really, by instead of you having a pipeline outside of your deployment environment that is pushing in changes constantly, every time you commit. Instead, you really run a daemon inside the cluster that pulls in things. So it's going from a push-based model to a pull-based model. This has a lot of benefits, one of them being that you don't have to export any secrets or credentials from your cluster to some sort of external continuous delivery system. Another one being that if anybody would go into your cluster and manually update a resource, for example, Flux would detect this drift between the source of truth, which is Git, and what's actually inside the cluster. It also means that when you want to audit and see, for example, what is currently deployed in your cluster, or who made a change and when a change was made, that could all be done in a Git repository, as Git keeps a history of changes. So Flux is built around a concept called Kubernetes controllers. Kubernetes controllers is this missing thing that I haven't really described yet, which is the last part of how custom resources works. So Flux consists of a couple of Kubernetes controllers. And what a controller does is it takes a specific resource kind and does work based on it. So what it's doing is it's running what's called a reconcile loop. So it's waiting for a specific resource kind for an action to be acted upon it. If it's a new resource being created, updated, deleted, whatever, it will then do the actual actions based upon that resource. So for full deployment of Flux, Flux consists of a set of applications called controllers that run inside your cluster, plus the custom resource definition manifests, plus any custom resources that you define, which then you add inside of your cluster. Controllers can be, with the help of some frameworks, be written in Go. The majority of Kubernetes controllers out there today are mostly written in Go. This works really nice, so as we'll show later, with writing Terraform providers. A lot of the tooling around Kubernetes controllers and Go is its framework. So you can use Go structs that generate custom resource definitions, so you're not writing these custom resource definitions. So installing Flux is actually a multi-step process. There are the simple parts of it, and that's adding the CRDs to your cluster. It's adding the controllers and maybe configuring the bootstrap process. The more complicated part is linking these things together with external sources. So to bootstrap Flux, you actually need a Git repository that contains the manifests for the controllers that are deploying itself. So it's kind of a circular bootstrap where you need to have their sources in both your cluster and your Git repository for things to work. After that's done, you can actually just commit things into this new Git repository you have and have it automatically be pulled down into your cluster. But this initial step has to be done for things to work. And that includes creating a Git repository, committing the CRDs and the manifests to that repo. But also, if you're running a private Git repository, you would need to create some sort of credential, if it's a HTTP or a SSH credential, that you both need to configure with your Git provider, but also then add to your cluster so that Flux has that credential that it can communicate with. To deal with all this complexity, really, we built a CLI called Flux, also that automates a lot of this process. So you'd give it your GitHub credentials or an API token, and it would basically deal with the whole deployment for you. And that worked for a lot of people. The issue turned out to be that a large part of the Flux community that were heavy Flux users were also Terraform users, because they were creating their Kubernetes clusters with Terraform. This created some sorts of friction between Terraform and Flux, as a lot of people would use null resources to shell out to the Flux CLI and have it then deal with the installation process. I'm personally not a big fan of running local exec with Terraform, mostly because it requires the computer or CD or CI system to have other dependencies installed, but also there is no way of really defining the versions of these dependencies. So the Flux version could be really whatever Flux version that happens to be installed. So you end up with different results between runs on different computers, but also it would be hard to, in an automatic way, detect when a new version is used, so that the null resource could be triggered. What most people would do is they would have a trigger causing the null resource to always be run. So this wasn't really a optimal solution. There are a lot of people who including myself, who liked to use Terraform to set up the cluster. So it was only logical that we needed a better solution for how we would create or how we would bootstrap these clusters, because we really wanted it to be a single seamless process of creating the cluster and then bootstrapping it with Flux. And then we could hand over the rest of the manifest deployment to Flux instead. So when working with Terraform and Kubernetes, you have a couple of options when it comes to providers. All these providers really end up doing very similar things. They connect to the Kubernetes API that you specify, and it's kind of nice to link together the Terraform that creates your cluster, and as an output, you would get the API endpoint and the credentials, and you'd pass it to your provider. But the most common, I guess, is the official HashiCorp Kubernetes provider. You write your Kubernetes resources as HCL instead of YAML, but it's really just a one-to-one relationship there. Nothing really special about it. The downside of the Kubernetes HashiCorp provider is that each resource or each Kubernetes kind has to be defined inside of the provider with all its parameters. This means that if any update in Kubernetes adds a new field to a resource kind, the provider itself would also have to be updated. But it also means that any custom resource is not available with this provider. It's only the core resource kinds that are possible with the Kubernetes provider. If you want to use custom resources or do a bit more dynamic stuff, there is a Helm provider. I won't go into too much detail, but Helm is a packaging templating engine for Kubernetes manifests that allows you to template YAML files, really. The benefit of using the Helm provider is that you can write pure YAML and have it run the manifest generation and basically allow it to deal with the deployment of it. There are some downsides with Helm. One of the major ones is that Helm does not manage CRDs for you. So if you want to actually add the custom resource definitions with Helm, it will only install the custom resource definitions, but it will not update them for you. Then there is a third-party provider called kubectl that allows you with Terraform to apply raw manifest files without really it knowing too much about what you're applying. According to me, it actually works pretty well. And then there is the kind of the interesting provider out there, which is the Kubernetes Alpha provider that is trying to solve the problems that the current production use Kubernetes provider has around, for example, not supporting custom resource definitions and having to be updated every time that the Kubernetes API is updated. So it's taking a different approach to how Kubernetes resources can be created with Terraform. But the issue with that is it really isn't production ready yet. And then, as I stated before, you have null resources, a last escape hatch. if you're really out of luck. It really isn't a great solution using null resources and shelling out, mostly because you would need to take your Kubernetes credentials and write it to a file and have that file live somewhere. But also it creates a dependency on a binary that really isn't explicitly stated by Terraform. Yeah, so looking around, within the Flux team, we were looking at how we're supposed to enable these types of use cases of creating Kubernetes clusters with Terraform, but also then installing Flux. One option was, writing a Helm chart. I think the major downside of writing Helm charts was really the lack of functionality around managing CRDs, as the Flux project creates a lot of CRDs, and these CRDs are constantly updated. We guess that we would end up in a situation where users would be very confused and bugs would be caused just because they would update the Helm chart version, but they wouldn't update the CRD versions. So there would be a drift there. So it would introduce a manual process that really wasn't that nice. Additionally, Helm charts required us to maintain yet another deployment method that couldn't really be automated. Another option was static manifests, just publishing the manifests and then allowing the community to, for example, use the kubectl provider to apply that to your cluster. It has its downsides of not really enabling any user configuration, but also it would be difficult to push and force updates for the Flux controller components, as my guess would be that a lot of users would copy these manifests and then have them live in their own Git repository, which would make the updating process a manual step. And last but not least, you would have the Kubernetes alpha provider, and we had a look at it, but it really isn't an option as it isn't production ready yet. But all of these three options really don't talk about the other complexities of installing Flux, which is integrating with, for example, GitHub and committing things and committing files. So alone, these three solutions wouldn't really solve the problem anyways. You'd still have to do a lot of other work. So the solution we came up with was writing a Terraform provider that would kind of fit the middle ground between doing everything and doing nothing. We had some initial discussions about whether the provider was going to deal with all the complexities in the same way that the CLI does. But my feeling really was that it kind of broke the idea of Terraform. So Terraform is great when you look at it from the perspective of the available providers out there and the way that different providers or outputs from one provider resource can be used as an input for another provider resource. You're really just standing on the shoulders of giants and building on top of prior art, really. So our solution was to create a very, very simple provider that has two data sources. And the only thing they really do is they output YAML strings. The benefit of this is that the provider can share the same code by importing it as a package as the CLI does. So whenever we update the CLI to generate the manifests in a different way or to add a different parameter, because the code is shared, all we need to do is just update this dependency, as both the projects are written in Go also. And we also then expose the same configuration parameters as the CLI bootstrap command does. So there isn't really a difference in functionality between the two solutions. So in this example here, we're going to show how everything kind of comes together with different providers. So here we can see the different variables that we have to configure: the GitHub user, GitHub token, repository name, a Git branch, and a target path, and the repository visibility. So these are kind of the default variables. If we check the main file, we can see that there are a bunch of providers. the GitHub provider we're using, and then the Kubernetes provider, the kubectl provider, obviously the Flux provider, and a kind provider. A kind is a project that allows you to run Kubernetes clusters locally in Docker. So we're creating a local Kubernetes cluster. And then you can see below that we're configuring the kubectl and Kubernetes providers to both connect to this local cluster that we've created. So below that, we're also creating a TLS key for SSH communication between the Git provider and Flux. And then we are using these custom data sources, the Flux install and FluxSync data source. The FluxSync data source is what configures the whole Git syncing as it takes the URL for the Git repository, and the Flux install contains the custom resource definitions and the controller components along with that. Then this is kind of where the complex parts happen. So we're using the kubectl provider which takes the output from the two data sources in raw YAML and applies it to the cluster. And then we're creating a Kubernetes secret with the TLS or with the SSH key. And last but not least, we're creating a GitHub repository and committing the files, as the GitHub provider allows you to commit files with Terraform, which is pretty nice. So if we're going to apply these changes, we can see that it's going to create a bunch of resources. Mostly these are just files. It's really not that much of an infrastructure Terraform example. And after a while, we should have everything applied and successfully created. So we can now see that we have access to a kind cluster or a Kubernetes local cluster running. And if we jump into the Flux system namespace, we can see that we now have 4 controllers, as we've talked a bit about before about the Flux controllers. And we can also see that there is a custom resource called Git repository that is synchronizing from the newly created GitHub repo that we created. And there is a customization resource that's taking that content and applying it to the cluster. We can also jump into GitHub and see this new Fleet Infra repo, this bootstrap repo that we created, and the files that are now present inside of the repository. Here, the Flux components are committed, which is basically a bunch of YAML containing all the custom resources that we need for Flux to work. And this is kind of becoming then obvious why we want to automate these types of things. And then we have our sync components, which is, as you can see here, the URL is pointing back to the same Git repository as we are in currently. And if you'd want to make any changes now, you could commit additional manifests to this repository, and they would be pulled down into the cluster. Another nice thing with this provider then is that if you'd want to change the version of Flux that you're using, all you need to do is go into your Terraform, and in the Flux install data source, you could add a version parameter that sets the version of Flux that's being used. So there are some downsides with the solution that we have built today within the Flux project. The solution isn't really that user-friendly from a UX perspective. There's a lot of Terraform that has to be written and a lot of providers that have to be combined with each other, and some Kubernetes magic that has to be done to get Terraform to ignore some of the changes that Flux does after the deployment. And we've been looking for a while now at how we can make the experience of installing Flux a lot easier. One of the things that I really don't like with the solution that we have built is how we, in a way, abuse a lot of the resource looping. I'll show a bit of that in the next slide, as we have to generate unique IDs for the different manifests that we're creating. And it's really taking the looping of resources to an edge where Terraform core starts to have some issues with dynamic variables, and it starts complaining about sometimes if you have an output that you pass to the data source that is computed, Terraform will fail because it doesn't think it knows the output of the data source before the plan. So you get all these really weird edge cases with the current solution. And the other thing is that people both either expect the data source to do more other than just output YAML, while at the same time, a lot of the bugs that are reported towards the provider are usually related to other providers, but it's mostly because of how providers are connected with each other. It's a difficult balance between making the use case or the UX very easy, while at the same time playing into the strengths of Terraform. And the strengths of Terraform is really the fact that there are so many providers out there already that do a lot of these types of things. So it would be very stupid from our perspective to re-implement providers that already exist out there. But part of the complexity, for example, here in this example, is how resources are looped. So this is from the demo that was just shown, and what basically is being done here is that the YAML that's outputted by the data source is in a multi-doc format. What that means is that there are multiple YAML documents within a single string. The kubectl provider does not allow you to apply these multi-doc YAMLs in a single shot in the same. That is different from how the kubectl CLI does, where the kubectl CLI allows you to apply multi-doc YAML without any issues. So what we have to do is we have to split the multi-doc YAML for this data source, the kubectl file documents data source, into separate YAML objects. The issue there is then that if we were to do a count and then loop on the count, the ordering of these YAML objects in this multi-doc YAML file would actually matter. So if the provider were to output YAML in a different order, it would cause Terraform to want to recreate all the different Kubernetes resources that are in the cluster, even if the actual resources themselves haven't changed. And that we've actually faced this issue initially before implementing this solution. So what we're doing here is really we're using a lot of metadata, API versions, and kind data from the every manifest to create a unique ID, which is used as a key for the resource. This works, but yet again, it's not really an optimal solution. And that's kind of what's gotten me to think about what other options are out there in the future. So looking forward, really, I think that there needs to be a better solution for Terraform providers out there, or a solution for Terraform to deploy Kubernetes controllers into Kubernetes, because the use case or the people using these types of things are already out there. There are people creating Kubernetes clusters with Terraform, and they're obviously they want to install controllers into these clusters. One option might be to build a more of a generic provider, Terraform provider, that would support multiple different controller projects out there, because they're all built on the same framework. So that would be an interesting solution to just, not only would we then support the Flux project, but we could support multiple projects without having to do extra work. Another solution that I have high hopes for is the Kubernetes Alpha provider. The way that the Kubernetes Alpha provider works today would actually work really nicely with Flux, as we could, and I've seen this being done, take YAML and generate HCL representations of the same YAML data, and then somehow export this to a Terraform module, for example. Terraform modules may introduce the same issues that Helm charts already have today, unless it can't be automated. But I think that there is a gap right now that has to be filled in the space of projects building controllers that are more close to infrastructure layers rather than application layers in a Kubernetes cluster, that a lot of people will want to deploy with Terraform, and maybe not even with Flux. Even there might be other controllers out there that people would opt to deploy with Terraform rather than Flux. So there is a large need of coming up with some sort of solution to enable this type of use case, and Flux would probably be the most extreme use case out there, as it has to integrate with Git, and you have to commit things with Terraform, which really doesn't make the thing make anything any simpler. And that was all that I had for today. Thank you for listening in. If you want to reach out to me, my contact details are down there. You can reach me on the CNCF Slack, or you can follow me on GitHub if you want to do that. Thank you all very much.